Welcome viewers. In this video we'll see the details about repulsion principle followed by repulsion motor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic repulsion principle, repulsion motor. First we will see conceptually what are the details available in the repulsion motor. Stator winding of the distributed non-salient pole type housed in the slots of a smooth cored stator. So is a distributed non-salient pole. Non-salient pole projection is not there. They are housed in the slots of smooth cored stator, just as in the case of split phase motor. The stator is generally wound for 4, 6 or 8 poles. So this is the detail about the stator. Now we'll see the rotor. The rotor slotted core type carrying a distributed winding, either lap winding or wave winding, which is connected to the commutator. The rotor is identical in construction to the DC armature. So rotor is very similar to the DC armature. Brushes, commutator, lap winding, wave winding is very similar to DC armature. Now we'll see the commutation process. A commutator which may be of one of the two types. First one is an axial commutator with bars parallel to the shaft. Axial commutator. Another one radial or vertical commutator having radial bar on which brushes press horizontally. One is axial commutator parallel to the shaft. Another one radial or vertical commutator having radial bar horizontal, brushes press horizontal. Carbon brushes fitted in carbon holder which ride against the commutator and are used for conducting current through the armature winding, that is rotor winding. So the commutator available mean automatically we have carbon brushes. So that fitted in the carbon brush holder with a ride against the commutator and used for current, conducting current through the armature winding. Now we'll see the repulsion principle. So we'll see the repulsion principle. To understand how torque is developed by repulsion principle, consider the diagram which shows a two-pole salient pole motor with magnetic axis vertical. For easy understanding, stator winding has been shown with concentrated salient pole construction. Right? Now we'll see the diagram. Two-pole salient pole with a magnetic axis vertical. We'll see the diagram now. So this is the two-pole salient. So this is the stator, top one. Then this is the rotor portion, and bottom we have another one more pole of the stator. So it is stamped as y dash. The axis is stamped as y dash. Right. So now we'll see the what happened in the rotor. So rotor, the brush holders, brushes are available. So these are all the EMF and current direction, plus and negative. So this brush holder, brush is available aligned vertical with the magnetic axis. It is available vertically. So this is the stator pole, N pole. This is the rotor, N pole. Both are same. Both stator as main pole as well as rotor pole having N at the top. Similarly, S at the bottom. So there is a repulsion will happen. Both will repel each other. So that is called a repulsion motor. The important thing is the brush holder aligned vertically. In that position only the EMF will be generated and current will be flowing through the rotor circuit because of the vertical position. Now we'll see what will happen in the horizontal position. So this diagram refers the horizontal position. The brush holder is available horizontally. Remaining all are same. At the top, main pole and rotor pole is N. Bottom, main pole and rotor pole is S. The axis is y dash. So in this case there is no EMF is induced. Only in vertical case the EMF induced when the brush holders are available in the horizontal mean the EMF is not induced. So this is therefore the diagram B, vertical position diagram B, vertical position diagram A, horizontal position diagram B. Now we'll go to the description. Right, so these two poles, alien pole, just now we referred. Now we'll go to the remaining description. The basic function of the machine will be same with the either type of construction. Both are almost same. Only the brush holders are different. Vertical diagram A, horizontal diagram B. As mentioned before, the armature is of standard DC construction with commutator and brushes. The armature is very similar to the DC motor. Suppose that the direction of flow of a alternating current in the exciting or field winding in such a way that it creates N pole at the top, S pole at the bottom. So that we'll discuss in the diagram itself. N pole is available at the top, S pole at the bottom because of the exciting, the direction of current and EMF. Based on that the poles are created. The alternating flux produced by the stator winding will induce the EMF in the armature conductor by transformer action. Right. So this alternating flux is produced by the armature winding will induce the EMF in the armature. So only in vertical position, brushes are vertical position, the EMF is induced. Horizontal position, EMF is not induced. That we refer in the diagram A and diagram B. Now we'll go to the next description. The direction of induced EMF can be found from Lenz's law and it is shown in the diagram. The EMF and current directions are shown in the diagram A. Diagram B, there is no EMF induced and current. That can be calculated by the Lenz's law. However, the direction of induced current in the armature conductor will depend on the position of the short-circuited brushes. So these short-circuited brushes will decide the induced EMF direction. That is in the vertical position, EMF is induced. Horizontal position, EMF is not induced. So this is based on the short-circuited brushes. If the brush axis collinear with the magnetic axis of the main pole, the direction of the induced current will be as shown in the diagram A. First diagram, vertical. The brush positions are aligned vertical. In that EMF is induced, that we refer in the diagram A. As a result, the armature will become an electromagnet with the N pole at the top, directly under the main pole, main N pole, and with S pole at the bottom directly over the main S pole. Right. So at the top, main pole is N and armature pole also N. At the bottom, main pole is S, armature pole also S. Now we'll refer the diagram once again. So this is the N pole, main N pole, rotor N pole at the top, rotor S pole, main S pole at the bottom. This is the diagram A. The brushes align vertically, so current directions are clearly indicated in this position. Now we'll go to the next position. So the top N pole, bottom S pole. Because of the face-to-face positioning of the main and induced pole, no torque will be developed. So at the top both are N pole, at the bottom both are S pole. So there is a repulsion takes place. So that induced magnetic pole and no torque will be developed. The two forces of repulsion on top and bottom along with YY direction, YY in direct opposition to each other. So that are opposing each other. Right. If brushes are shifted through 90 degree, that is diagram B, the brushes are held in a horizontal to the position shown in diagram, so that the brush axis at the right angle to the magnetic axis of the main pole. The direction of induced EMF voltages at any time in respect to the armature conductor are exactly same as they were for the brush position of diagram B. Right. So in the next what we are doing, we are shifting the shifted to 90 degree. Brush positions are shifted so that the brush and the brush axis is right angle to the magnetic axis at 90 degree. So the direction of induced voltage at any time in respect to the armature conductor is very similar to that is given in the diagram B. Now we'll refer the diagram B. So this is the diagram B. So this is the main axis, magnetic axis, brush axis, both are 90 degree. It is displaced at 90 degree. Refer diagram B. So now we refer the diagram B. However, with brush position of diagram B, the voltages induced in the armature conductor in each path between the brush terminal will neutralize each other. That's why we already discussed. In vertical position, EMF induced with the direction also given in the diagram A. In horizontal position, there is no induced EMF, so that there is no current direction given in diagram B, right? So in diagram B, horizontal magnetic axis and brush holders are 90 degree to each other, but it will produce both induced EMF and armature current, but it is neutralize each other. Hence there will be no net voltage across brushes to produce the armature current, right? Diagram A and B very similar. Diagram B also, it will induce the EMF, but that is neutralize each other, so there is no possibility of flow of current. I will see the remaining. If there is no armature current, obviously no torque will be developed. If the brushes are set in the position as shown in the diagram A, so that brush axis in neither in the line nor 90 degree from the magnetic axis YY of the main pole, a net voltage will be induced between the brush terminal, which will produce the armature current, right? So in position A only will the EMF will be induced, the armature current is flowing. B also it will same, but it is neutralized. The armature will again act an electromagnetic, it develop its own N and S pole, which in that case will not directly face the respective main poles, right? Again it will develop the electromagnetic and develop its own N and S pole, right? Now we'll see the another one more diagram. Now we discuss vertical position, horizontal position. In between, inclined, if it is inclined with angle alpha. So as shown in diagram C, the armature poles lie along AA, making an angle of alpha with YY, right? So there is a angle, horizontal, vertical is there. In between, now it is having with an angle of alpha. That refers the diagram C. Now we'll see the diagram C will refer. So this is refer the diagram C. The top we have N pole, what we discussed earlier. At the bottom S pole. The axis is Y dash, diagram C. Now the rotor is having an angle of alpha, this AA dash and YY dash. Between YY dash and AA dash there is an angle of alpha. So in this position also there is a EMF will be induced and the motor rotates. So that refers in the diagram D. See this. So this inclined, now it is inclined. Earlier case, the diagram A, here also main pole N, rotor pole also N. Rotor pole S and main pole is S. So there is a repulsion. Now it is rotated. It is inclined angle of alpha. So now see the position. This diagram D refers. This S pole and N pole. Now it is rotor is with an angle of alpha. So this S and N attract each other. This N and S will attract each other. So it will start rotate. So this direction indicated as in the diagram, it starts rotates, right? So this diagram C shows the rotor position with an angle alpha. Diagram D will shows how it is attracted and what is the direction of rotation. Now we'll see the description. Hence the rotor N pole will be repelled by main N pole, and rotor S pole will similarly be repelled by the main S pole. Right? Attracted as well as repulsion also takes place. Consequently, the rotor will rotate in clockwise direction as shown in the diagram D. Now we will refer the diagram D again. So these two are attracted, not only these two are repelled each other. So this main thing is the repulsion motor. There is a repulsion takes place between these two, main N pole and rotor N pole. Similarly, main S pole and rotor S pole. So there is a repulsion takes place so that it rotating in the clockwise direction. Mainly we are focusing repulsion, not a attraction. Right? This repulsion motor, so that the basic principle repulsion. So there is a repulsion that takes place between main and rotor pole here also. Yes, both are yes, repulsion takes place. Since the forces are those repulsion, it is appropriate to call the motor as repulsion motor. Because of this, called as a repulsion motor. So principal shortcoming as of such motors are. So what we discussed, the brief discussion is given. Speed varies with changing load, becoming dangerously high at no load. So the speed which varies, changing load is changes means speed will vary. That will be dangerous at the no load. So we have more speed is there. So we need to check the no load is there, then dangerous speed will be there. Low power factor except at high speed. High speed means no problem. If it is low speed means the power factor will be low. Tendency to spark at brushes. It's a common problem. As a DC motor having common problem, sparking. So here also the sparking is occurs. Now we'll see some more details about the repulsion motor. Speed, torque characteristics and other. And what is the current and torque direction. We'll see. Now we'll see the speed torque characteristics followed by the direction of torque and speed. It should be noted that if the brushes are shifted counterclockwise from y dash, rotation will be also the counterclockwise. So the rotation of motor based on the rotation of the brushes. Obviously the direction of rotation of the motor is determined by the position of the brushes with respect to the main magnetic axis. Right? So the rotation is based on the brushes with respect to the magnetic axis. Now we'll refer the diagram. So this diagram is given, only the rotor portion is there. This is stator available. Refer the diagram E. So this is the direction of rotation clockwise. Then the alpha angle, that is the angle between main axis and brush axis, alpha. So this alpha also determine the torque. Torque developed by the motor is determined by the alpha. We discussed the magnetic axis is vertical, the current and EMF will be generated. If it is horizontal, EMF will be generated but it is neutralized. In between, with the inclined angle between main axis and brushes, that is nothing but alpha. In that, the torque is keep on increases. Right? So this diagram will give the direction of rotation of the motor, direction of rotation of the torque, and direction of rotation of the angle alpha. That is, alpha is the angle between main magnetic axis and brushes. So this refer the diagram E. Then diagram F is there, that is the speed torque characteristics. Rotation angle is available in the x-axis, in y-axis torque is there. So the torque increases gradually and reaches the maximum value, thereby decreases and reaches 0 at 90 degree. So it is rotating from 0 to 90 degree. At 0 degree itself having more amount of torque is there. Almost between 45 degree it reaches the maximum value, thereby decreases and become 0. So the 0 degree itself, that is the brushes are aligned with main magnetic axis. At that time itself the torque is available, thereby increases. When the alpha increases, it also increases and reaches maximum value, then by decreases. That is almost 0 to 45 degree. It is increases, thereby decreases. This refer the diagram E. Now we'll go to the description. It is worth noting that the value of starting torque developed by such motor will depends on the amount of brush shift. So the torque is purely based on the amount of the brush shift. How much brush shifted, that much of torque is developed. Whereas the direction of rotation depends upon the direction of the shift. Direction of rotation and direction of shift are all the same. So that only we refer in the diagram E. Maximum starting torque is developed at the some position where the brush axis make an angle lying with 0 to 45 degree with the magnetic axis of the main pole. At 0 degree itself, some of the torque is available, thereby increases and reaches maximum value, then decreases. So between 0 to 45, we are getting the maximum torque value that we referred in the diagram. Now we'll see the further detail. Motor speed can also be controlled by means of brush shift. So brush shift, so already we discussed, torque is depends upon the amount of brush shift. The direction of motor is direction of the brush shift. So the speed is controlled by brush shift also, right? So shifting of the brushes will control the motor speed. Variation of starting torque of a repulsion motor with the brush shift is shown in diagram F that we discussed in the diagram. So the diagram between the torque and angle alpha. Then a straight repulsion motor has a starting torque about 350% and moderate current about 3 to 4 times of the full load value. So the torque is about 350%. The starting current is 3 to 4 times of full load value. So in this video we discuss the repulsion motor. What is meant by repulsion principle? What is the construction of the repulsion motor? What is the magnetic axis? Vertical, thereby horizontal, thereby inclined with an angle alpha. In 3 cases, how the torque is produced. Then we discuss the torque versus angle, or how the torque is increases. Then so all the details we discussed in this about the repulsion motor along with the repulsion principle. There is a repulsion between the stator pole and rotor pole. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination.